Jeffrey, and let's welcome our next speaker, Adam Palmer from UNC.
All right. Thank you for the invitation to present here today. Right, so yes, I'm Adam Palmer at UNC, and developing better cancer treatments at the end of all of the research requires a human clinical trial to show improved efficacy in a population of patients. So a really practical output for mathematical oncology then is methods that could identify which treatments will be successful or unsuccessful in clinical trials. And I will present methods to address this question in the specific case of drug combinations used to treat advanced cancer. So most types of advanced cancer are treated with drug combinations. Curative regimens and settings where they exist nearly always involve drug combinations. And the need for that is that monotherapy just isn't good enough. It's typically seen that using a single chemotherapy could induce responses in some fraction of patients, but not all. And even when there is a response, it kills some fraction of the cancer cells, and some fraction are left and grow back, commonly having resistance. So combinations of active therapies can help this in two different ways. First, patients who are resistant to drug A might respond to a drug with a different mechanism B, and thereby increase response rate in the population. And in patients where two drugs do work, they could kill a larger fraction of cancer cells. For the same logic, cells that survive drug A might get killed by a different drug B. Another mechanism is that there could be synergistic drug interactions where they modulate one another's effects so that the combination has an effect that is more than the sum of its parts. But I hope you see here that sizable improvements in outcome could be achieved in the absence of drug-drug interactions when active therapies are being combined. So when we're talking about clinical trial results, these outcomes are these survival distributions or Kaplan-Meier curves. So here is an example in metastatic melanoma showing the percentage of patients who are free of disease progression over time when treated with one of two different checkpoint inhibitors or the combination of both of them in the green line. And actually, so this concept here about the interpatient variation and increasing response rate, an equation was published in 1960 describing how you could calculate the expected response rate from multi-drug combinations according to this principle. And a few years ago, I showed that this concept is also applicable to progression-free survival data. So we have this simple equation that says maybe drug A works, or if drug A fails, maybe drug B works. And that makes very accurate predictions of phase 3 trial results in a variety of settings. After that paper was published, we then applied that to, in a follow-up article, looking at a whole lot of clinical trial results that came out afterwards in the setting of immune checkpoint inhibitors combined with other agents. And so on all of those Kaplan-Meier curves there, the black line is the model prediction based on monotherapy. The blue lines are the phase 3 clinical trial results. It's one in the bottom corner that underperformed because it was very poorly tolerated, but all the tolerable combinations were statistically indistinguishable from the model expectation. We can also look at that as a scatter plot of observed versus expected progression-free survival at 12 months. And so across all these different cancer types, not all of these trials met their efficacy endpoints. So some led to FDA approval, some didn't, but they were all pretty close to what was expected by this model. And so given that these trial results came after the model was published, this is 9 FDA approvals that have prospectively validated the model. But this here is just describing the effect of which one drug works best for an individual patient. It's not even describing an additive effect of two drugs in individual patients. This is just saying that at 12 months, maybe drug A got you to 12 months, or maybe drug B got you to 12 months. And so we wanted to consider next, what about additive effects or synergistic effects? And the issue here is that clinical synergism has never been precisely defined. It's been written about for decades that there isn't an understanding of what this term means in clinical trial results. So there have been tens of thousands of articles quantifying synergy in various ways in preclinical systems. It has been clearly written in oncology textbooks that synergy means more than additivity, but what's additivity in humans? So Hannah Huangbo in my lab has developed a method where we say, well, let's take the time to disease progression and add those up. And really the null hypothesis here is that if you have some drug B being added to a cocktail with A, that drug B prolongs progression-free survival in that combination to the same degree that it would prolong progression-free survival if it was used as a single agent, compared to giving nothing. It is important here to recognize that with progression-free survival, it takes some time to observe progression, even in the absence of any therapy. Usually the first radiological scan is around 8 weeks. So if you had 3 different drugs that all showed progression at 2 months, you shouldn't say 2 + 2 + 2 = 6. That progression at 2 months means it did nothing. So we subtract the first scan time so that we're not really double counting that. So the other part about applying this model is that you can't describe the effect of a drug as like 6 months progression-free survival because it's a distribution. So what we're really doing here with drug additivity in a human population is the sum of variables, right? You've got a distribution of PFS times for drug A and a distribution for drug B. And the familiar example of adding variables is rolling 2 dice and adding them up. So it's a similar process here to calculate the expected progression-free survival distribution if the effects are additive. So Hannah went and looked at all FDA-approved drug combinations for advanced cancer over a 25-year interval and found all the cases where there were dose-matched monotherapy data. If we don't have monotherapy data, we can't apply the model. So this is 37 different FDA-approved drug combinations, all these Kaplan-Meier curves. The black lines are the clinical trial results. The red lines are the predicted effect of additivity. 5% of them were significantly more than additive. 95% were additive or less. Most of them in the green there are statistically indistinguishable from the additivity model. So we can also look at these as a scatter plot of observed versus expected effect. So every one of those Kaplan-Meier curves is replotted now, where if it's a straight line on the diagonal, it's doing exactly what the model predicts. So the major source of error here is that some are less than additive, but it is still the case across 25 years of approvals that 100% of the approved drug combinations in this data set were predicted by this model to beat the control arm and produce a statistically significant improvement in PFS. So we next asked, can this discriminate between trials that succeed or fail? So we looked at a 5-year interval of just all published phase 3 trials of drug combinations, positive or negative. So every green dot there is a successful phase 3 trial that improved PFS. All the purple dots are phase 3 trials that did not significantly improve PFS, and they're ranked according to whether they were predicted to have a statistically significant improvement in progression-free survival. So you can see most of the successful dots on the green there were absolutely confidently expected to succeed. And the majority of the unsuccessful trials were also quite confidently expected to fail. And if you look at that as an area under the receiver operator curve, it's an area under the curve of 0.92 with 100% sensitivity and 78% specificity, meaning most failed phase 3 trials are predictable failures. And the model is just adding the clinically observed effects. There's no parameter fitting or training set. So adding up progression-free survival times, this works for a lot of use cases here. This can't explain cure, where we're not just like pushing out time, but making disease never come back. But we can think about the same concept on this scale of fraction of tumor cells that are alive. And this was actually a calculation done in the 1950s and 60s, where it was described that if you think about the number of cancer cells on a logarithmic scale. So data, for example, in acute lymphocytic leukemia showed that when one drug worked really well, you could get about a 99.9% tumor cell kill, or 3 order of magnitude reduction. And they said, in theory, then 4 such drugs could cure acute leukemia. And this motivated a trial, and they did cure a few patients with 4 drug combinations, but not most. So a paper by Amy Pomeroy in my lab, we revisited this considering that effect sizes are variable, and drug combinations are therefore these sort of sums of variable effects. And so we took the clinical efficacy of single agents against pediatric acute leukemia and did this model of sort of adding them up. And the implication of this model was that you expect a few cures with a 4-drug combination. And it takes more and more drugs to sort of shift that distribution of the number of tumor cells so that more and more patients are completely cured. And this describes very nicely the historically observed response rates and cure rates. This is a very simple model. I think of this more of like a quantitative illustration of concepts about inter and intra-patient heterogeneity. But there's no kinetics in this. So we wanted to get more kinetically detailed with these models, and we took our inspiration from an approach in pharmacokinetics where dynamic models can describe drug concentration over time. But then once you're talking about human populations, all these rate constants are variable, like drug elimination rates are variable between people. But they can be described by distributions. And this is what supports the science of population pharmacokinetics, which has been an industry standard method for about 50 years now. where you take these dynamic models and you consider that all the parameters follow a distribution, and you can then describe the sort of distribution of kinetic profiles in human populations. The beauty of this is you don't need to know why a drug clearance rate is higher or lower in some patients. You just empirically fit the human data. And so all the sources of complexity that happen in reality, they are implicitly present in the calibrated model, even though you're not explicitly modeling what the mechanism of it is. So we applied this also to models of like tumor kinetics in response to drug treatment. For example, this sort of fractional kill and then resistance growing out, sort of models of population tumor kinetics. The other thing we added to this was that within a tumor, there's heterogeneity. And so probably many of you have seen this before, these illustrations of like fractional kill. Every cycle of treatment kills some percentage of cancer cells. This would be true if the tumor was completely homogeneous and never evolved and there wasn't any resistance. And this is often modified with like a two population model, some resistant, some sensitive. If you were to measure drug sensitivity, if you took like 1 million clones and measured their level of drug sensitivity, you wouldn't see just two populations, you'd see a distribution. And I particularly believe that because I did the experiment and saw a distribution for the drugs that are used to treat diffuse large B-cell lymphoma. So then in the model, then you've got this distribution of drug response functions. And so what happens then is that with every cycle of therapy, this distribution is shifting and become increasingly drug resistant. And so every cycle of therapy is less and less effective. And then you can describe interpatient heterogeneity, saying, well, in different patients, the sort of middle of that distribution is at different points. So this is a way of describing quantitative variation in both interpatient and intratumor heterogeneity, sort of continuous variation in like clinical outcome. So Amy Pomeroy in my lab applied this approach to diffuse large B-cell lymphoma, where in every patient we're modeling this virtual tumor with distributions of drug sensitivities within it. And it's a multidimensional distribution for multiple drugs. And then that's put into a virtual patient cohort where you can get some patients are cured, some patients relapse at various times. And that then simulates a whole clinical trial. So the output of this is a Kaplan-Meier curve. But here we're not just like taking numbers from a trial, but every event in that simulated Kaplan-Meier curve comes from these simulated response kinetics. And actually applied this, calibrated it to the data for the standard R-CHOP therapy, as well as a new drug, polatuzumab, and simulated a clinical trial that added polatuzumab to R-CHP and posted the results online before the phase 3 trial result was published. And when the phase 3 trial result came out, it was exceptionally close to the result of the simulation. Amy then afterwards looked at this and applied this retrospectively to the last 20 years worth of trials in diffuse large B-cell lymphoma, where since the standard treatment R-CHOP was developed 20 years ago, just every attempt to add drugs to it had failed. And with this model framework, based on the individual activity of all of those other drugs, they were all expected to fail. The only thing that was expected to succeed was the one that did succeed and was FDA approved about 2 weeks ago. So in conclusion, I've shown you that the efficacy of drug combinations in clinical trials can be accurately predicted. The central concept here is that from multi-drug response distributions can be calculated from clinically measured single drug response distributions. We've also seen most of the best combination therapies, even curative ones, have effects that are quantitatively consistent with additivity. And we've looked at both retrospective analysis of trials, a number of prospective validation. Collectively, it's performing about as well or better than modern weather forecasting. So I believe the accuracy of these trial simulations are ready at this point to be used for prospective trial design. Thank you very much. I especially want to thank all of the wonderful members of my lab who've done all this work. Lots more cool stuff that they've done that I didn't have time to talk about. Thank you very much.
So it seems like the obvious implication here, right, is if we come up with enough drugs, then we cure cancer, right?
Well, magnitude of effect matters and tolerability matters. So if I take that pediatric acute leukemia model and calibrate that on the kind of anti-tumor effect that you get in like pancreatic cancer, the implication of the model is that none of the drugs we have are anywhere near ready to be able to cure advanced pancreatic cancer. Right, so
just because they're individually not effective enough.
Yeah, magnitudes of effective individual drugs just don't add up to enough. Although this sort of partly explains the difference why some things are incurable when they're metastatic, but they are curable in an adjuvant setting, because maybe there's enough activity to kill, 1,000 cells in a micrometastasis, but it's not enough to get rid of 100 billion cells in metastatic disease.
Thanks.
Yeah.
Hey, very nice talk. As can you go back to the slides where you are looking at the additive effects versus like fairly in the beginning
Yeah.
with like 9 curves or something like that, or 9 graphs. So yes, here.
Yeah.
So I don't know, maybe it's just me being trained as a mathematician, but I was very surprised to actually see this additivity. And I'm wondering if, you know, in the beginning, these curves are very nicely aligned and they follow each other, mostly in the beginning, but then they start to diverge.
Yes.
And
this is sample size drops as you go along the curve, not just because patients have disease progression, but there's censoring events.
yes.
So when you get to the ends of that, I haven't published all the at-risk tables because it wouldn't fit here. But as you get towards the end, when you see big steps, it gets very kind of jumpy at the end because there's very few patients on the trial.
Gotcha. Okay.
Yeah.
Yeah, because I was curious to see if there would be any sort of information about when these curves start to diverge, and what does it tell us about the status of the tumor? Would it become more heterogeneous? Would it be like, what is there actually? But
yeah, I think this is on most available data. This just comes down to statistical
Yes.
noise, and the Cox progression model takes that into account. And by the Cox progression model, these things are not statistically distinct.
Gotcha. Okay, thank you.
I believe there's real biology going on as time goes by, and we just don't have granular enough data to quantify the difference.
Yep.
Yep.
Cool. Thank you.
That's pretty phenomenal.
Thank you.
Very exciting. And I'm wondering about whether or not there are lessons that might be learned about what kind of combinations work. So going back to the pediatric leukemia, it was about non-overlapping toxicity and different mechanisms of action.
Yes.
And that's been a principle that's guided almost everything. And the advent of targeted therapies is really the first opportunity to look at the combinations of something very specific to a single mutation, let's say, in combination with things that might be DNA damaging or antimetabolites. So I'm wondering whether or not your results, and particularly those where the predictions didn't match the clinical data, can be informative about what kinds of combinations of drugs actually are best modeled, and why the ones that aren't best modeled aren't better modeled.
So we tried some analyses sort of splitting them up into like all the combinations that do or don't have an immune checkpoint inhibitor, everything that does or doesn't have an anti-angiogenic agent and so on. And we didn't spot any statistically significant differences in groups like that. Certainly on the like synergistic side of things, there's too few there to say anything systematic about it. I think to your point about with targeted therapies, there's more opportunity to kind of double hit the same thing like multiple HER2 antibodies or like BRAF and MEK inhibitors and so forth. And within that setting, these are all cases where the successful combinations of that sort have been agents that are very highly active as single agents, like trastuzumab and pertuzumab are both active single agents. Trametinib and dabrafenib are both active single agents. And so even in the cases where they're sort of double hitting the same process, the magnitude of clinical benefit doesn't seem to be deviating a whole lot from what's expected, even when there clearly are molecular interactions. And so I think sort of the historical principles of the way I see it is that safe and effective drug combinations are made by combining safe and effective drugs. I think that still broadly holds true.
That's fantastic.
Even if sometimes you can get multiple safe and effective ways of hitting the same Achilles heel. This doesn't mean there's no value in like double hitting one really key vulnerability, as long as those are both safe and effective agents.
Very cool.
One last question. Actually,
All right. Thank you.
Let's thank Adam.